Okay, so in the last video we talked about the Thomson model of the atom, the Geiger-Morrison experiment that led to the development of the Rutherford model of the atom, and today we're going to be talking about the Bohr model of the atom. Okay, now the Bohr model and the Rutherford model both have something in common. They both have a nucleus. Okay, but the difference between the Bohr model and the Rutherford model is that in the Rutherford model, remember you had that issue with stability where the electrons would spiral into the nucleus and blow up the atom. That would be bad. In the Bohr model of the atom, basically what Bohr said is, okay, we still have the electrons, we still have the nucleus, but the electrons are only allowed to exist in certain orbits. Okay, and they cannot exist anywhere in between. Okay, so this is basically what the Bohr model looks like, this top picture. And in the bottom picture, you can see the Rutherford model versus the Bohr model. In the Bohr model, you have these circular orbits, and the electron can jump, like teleport, from one orbit to another orbit, but it's not physically possible to exist in between in Bohr's model of the atom. Now, you might say, that's kind of weird, teleporting electrons. That doesn't seem right. And Bohr's model is not correct, obviously, but it is more correct than Rutherford's model of the atom because it at least explains some things that Rutherford's model was not able to explain. Okay, so in Bohr's model, you have these electrons orbiting the nucleus, and the electrons can only exist in these certain allowed orbits. Now, to go on from there, the electrons can actually jump from one orbit to another orbit. Okay, let's talk more about that. Now, in the Bohr model of the atom, electrons typically spend their time in what's called the ground state. The ground state, when we talk about the ground state, we're talking about the lowest possible energy orbit that the electron can have. And that's always going to be the orbit closest to the nucleus. So for example, in this top picture right here, the electron is currently in the ground state, that closest circle. And then as you go higher up, you get farther away from the nucleus, you're going up from the ground state. Okay, so electrons typically spend their time in the ground state, but they are allowed to move up to higher orbits. Okay, it's called becoming excited. The electrons can become excited, and the way they do that is by gaining energy. And the way they gain energy, or one of the ways they gain energy, is by absorbing, that means taking in certain types of photons. Now at this point you might be asking yourself, what the heck is a photon? We'll talk more about photons momentarily. Okay, but the electrons, if they take in this extra energy from a photon, they can go up to a higher energy level. Okay, so here you can see in this top picture the electron is orbiting in a circle, it's happy in the ground state, photon comes in, photon hits the electron takes all that energy that the photon has and goes boop, and it goes up to a higher energy level. This is above the ground state, and now it's in the second ring going around the nucleus. Now, what can happen then, and what does happen then, is the electron doesn't really want to be excited. It actually wants to go back down to the ground state. So after a little bit of time, it's going to fall back down and it's going to de-excite, or go down to lower energy. But when it does that, it has to do something with all the energy it's losing. And so the electron can only move down to a lower orbit by emitting or giving off certain types of photons. Okay. Again, at this point, you might be asking, what the heck is a photon? We'll talk about that in a couple minutes. So here, if you look at this bottom picture, and again, this is all about the Bohr model. The electron was going around in the second energy level, and at some point, it gave off a photon. There you can see the photon flying off. And then when it did that, because the electron lost energy, it was allowed to go back down to the ground state, and now it's happy in the ground state. Okay, now keep in mind that for most atoms, the electron wants to be in the ground state. So if the electron becomes excited and it gets knocked up, eventually it's going to fall down on its own. Just because the electron doesn't want to be excited, it actually wants to stay in the ground state. But in order to become excited, it has to take a photon in and absorb a photon and use its energy to go up. And when it falls back down, the only way it can fall back down is by giving off or emitting a photon. Okay, so just to give you an idea. Okay, let's take a look at a simulation really quickly. Okay, so here we have the Bohr model of the atom, as you can see. Okay, and what you see, that red dot there is basically the nucleus, and the electron is kind of orbiting. Notice that it's currently in the ground state. It's in the lowest possible energy level. Okay, so this is called the ground state, or what we might call n equals 1. Now what I'm going to do is I'm going to shoot a whole bunch of photons at this electron and watch what happens. Now again, we haven't talked about what a photon is, but basically a photon is a particle of light. So I'm going to basically shoot white light that has all different colors at this electron and watch what happens. Okay, so coming in from the bottom are these particles of light, these photons, and watch what happens if one hits the electron. Okay. Boom. Okay, now let me pause it right there. That photon a second ago hit the electron. I'm trying to see where the electron is now. Oh, it's way out here. And so it got knocked out from n equals 1, which is the ground state, all the way up to n equals 6. Okay, which is not the highest energy level. Technically, you can go up to n equals infinity, but usually you only see like, maybe 6 or 7 at the most. Now, this electron is excited, and it wants to go back down to a lower energy level, but to do so, it has to emit a photon. Now, this electron that's at n equals 6, it doesn't have to go all the way back down to n equals 1. It can go to any lower energy level that it wants. Okay, in fact, it's completely random. There's no way to predict which energy level it's going to go to. Okay, it can go from 6 to 5, from 6 to 4, from 6 to 3, 6 to 2, 6 to 1. And each of those different transitions I just named is going to emit a different photon. That means it's going to give off a different particle of light. Now, this might seem kind of abstract, but in chemistry, if you ever saw the experiment where you have like different color fires, your teacher might have like put different salts in a flame and produced different color fires. That's basically what we're talking about. Different elements give off different lights when you heat them up. And so those photons are light. That's what we're talking about here. Okay, so the electron fell back down. If you look at where it is now, it's at n equals 4. So it went from 6 to 4, and in the process, it emitted a photon. And now it's at n equals 4. It's still excited. It's just not as excited. In just a second, it's going to go to a lower energy level because it wants to get back to ground state, and it's going to emit a photon when it does that. Okay, and there it emits a photon. Now it's at n equals 3. In a second, it's either going to go from 3 to 2 or 3 to 1, I don't know, and it's going to emit a different photon. Okay, now it's back down to ground state, and the electron is going to stay there until it becomes excited again. Now I turned off the light, which is why there's no more photons. Okay, but that's basically how the Bohr model works. The electrons can take in and absorb photons and get promoted and excited up to higher energy levels, and when they fall back down, they have to give off that energy in order to go back down to a lower energy level. Okay, so that is the Bohr model. Now again, what is a photon? A photon is a particle of light. And so based off of the wavelength and frequency of light, different photons can have different amounts of energy and fall along the electromagnetic spectrum in different locations. Now, we didn't talk about the electromagnetic spectrum, but I'll show you a brief picture of the electromagnetic spectrum in just a second. Now, one thing you need to be very aware of. In the past unit, when we talked about energy, we talked about joules. Now, it is possible to measure photon energy in joules. But the problem is the energies are so tiny that even though we can use joules, it's kind of annoying to use joules to talk about photon energy. And so we use a different unit of energy to talk about photons, what we call EV, or electron volts. Okay, and so 1 electron volt is basically a tiny bit of energy. So when you see electron volts, just know that is a unit of energy that's way smaller than the joule. Okay, and that's why we're using it. Okay, so there's different parts of the electromagnetic spectrum. You have radio waves, you have microwaves, infrared, visible light, what we humans can see with our eyes, ultraviolet, X-rays, gamma rays. You might have heard of some of these things before. These things are basically all the exact same thing, and the only difference between them is their energy and their frequency and their wavelengths. Okay, so the only difference between a radio wave and an X-ray is the wavelength. X-rays have a much smaller wavelength than radio waves. That's literally the only difference between them. aside from that, they're the exact same thing. However, what that means is because they have different wavelengths and frequencies, they have different amounts of energy. And so this chart here basically shows you from lowest energy to highest energy. Radio waves tend to have the lowest energy. Gamma rays tend to have the highest energy. Okay, and so if you think, um, microwaves, people are scared of microwaves giving you cancer, but microwaves actually have very, very low amounts of energy compared to other parts of the electromagnetic spectrum. And so that's actually not possible. Microwaves can't give you cancer. Those photons just don't have the energy to do so. Okay, and so you might have heard when you were younger, like, don't stand next to the microwave, you'll get cancer. That's not possible. Like I said, microwaves, just looking at this chart, they don't have nearly enough energy to cause that kind of damage to your cells. Okay, X-rays do. Ultraviolet photons, some of those do have enough energy to give you cancer. That's why you have to wear sunscreen when you go outside, because the sun produces a lot of ultraviolet radiation. But you can have photons all along this part of the spectrum. Just a quick question. Based on the previous chart, explain which part of the EM spectrum has the highest frequency and which part has the highest wavelength. Okay, so I'm going to go back, pause it here if you need to look at this. Okay, so based off of this chart, explain which part of the EM spectrum has the highest frequency. Well, that would definitely be the gamma rays at the bottom that also has the highest energy. You can also look and you can visually see how the frequency gets way higher, the wavelength gets smaller when you go to this side of the chart. Which side has the highest wavelength? That would be radio waves. Example 4, based on the previous chart, which of the following photons would have more energy? Visible light or radio waves? Well, if this is from lowest energy to highest energy, visible light has more energy than radio waves because it's lower on the chart. Microwaves or X-rays? X-rays have way, way, way more energy than microwaves. Not even close. Okay, that's, by the way, that's why when you go to the dentist, you have to put that lead vest over you to protect you from the X-rays, because X-ray photons have so much energy, those can give you cancer. Those are actually dangerous to you. And infrared or ultraviolet. Okay, ultraviolet photons have more energy than infrared. Remember, infrared photons we perceive as heat. We talked about that in the thermodynamics unit. So when you talk about infrared photons, you're talking about heat. Okay, which, that sounds like it has a lot of energy, but it really doesn't. Okay, so let's finish up and talk more about some calculations in just a second. You don't need to know this conversion factor, but you do need to know that 1 electron volt is a very small amount of energy. And we talked about this before. In fact, I think this is the exact same slide that we looked at before about the Bohr model and how electrons can move, up and down in energy by absorbing or emitting photons. Okay, now let's talk more about how this works. In order for an incoming photon to excite an electron to a higher energy level, it has to have the correct amount of energy. Okay, what do I mean correct amount of energy? The energy the photon has in order to do the exciting has to have an energy equal to the difference between the two energy levels. And when I say the difference, I mean that in two different ways. I mean difference like the math word difference, like subtraction, or I mean the difference like the size of the gap between the two energy levels. And that'll make more sense in just a second. Okay, so in order to excite an electron, the incoming photon has to have the energy equal to the difference between two energy levels. When the electron gets de-excited and it falls back down to a lower energy, it emits a photon. And that photon has an energy equal again to the difference, or the gap, between the two energy levels. Okay, so let's do some examples so you can see exactly what that means, and then you can work on your practice worksheet in your quiz. So here is an example. Based on the diagram to the right, which of the following transitions could cause a photon of energy 0.31 eV, remember eV is electron volt, that's the unit of energy, to be emitted? Okay, remember emitted means given off. Now the only possible way for a photon to be emitted is if the electron goes down from a higher energy to a lower energy level. Okay, so first of all, we need to see which of these answer choices are downward transitions from a higher energy to a lower energy. Well, we can eliminate A because from 1 to 2 is obviously not from high to low. We can also eliminate C, and then we can eliminate E for the same reasons. Now, how do we know which energy transition is going to give us this special photon? Well, the photon is emitted with an energy equal to the difference between two energy levels. So basically, we need to see which two energy levels have a gap size of 0.31. Okay, if you look at this chart of energy levels, you'll see there's numbers on here. And we want to basically do some subtraction and see where is there a gap of size 0.31. So let's look at B. B says from n equals 2 to n equals 1. What is the size of this gap? Okay, I'm just going to subtract the numbers without the negative signs because I don't really care about negative signs. I want to know the size of the gap between them. So I'm going to subtract these two numbers, 13.59 minus 3.4. Again, I don't care about negative signs. I want the actual size of the gap. So if you subtract those two numbers, let's see, that is going to be 10.19 electron volts. So if, in other words, an electron going from n equals 2 to n equals 1 would emit a photon with this amount of energy. Well, that's not what we want. We want 0.31. So we can eliminate not D. We can eliminate B. And let's check out from n equals 5 to n equals 4. Okay. Again, I want the size of the gap between n equals 5 and n equals 4. So I'm going to subtract those two numbers, not caring about minus signs. Okay, 0.85 minus 0.54. Okay, and if you do that correctly, you should get a gap of 0.31 electron volts. Okay, and so that is actually the correct answer. The correct answer is D for example 6. Pause it there and look at that if you need to. Okay, so let's go on to example 7. Example 7 says, look at the energy level diagram to the right. In order to knock an electron from n equals 1, which is the ground state, to n equals 2, how much energy must an incoming photon possess? Well, let's look at the gap size, because remember, if the electron is sitting in ground state, n equals 1, in order for it to get excited up to n equals 2, a photon has to come in and hit it. And that photon has to have an energy equal to the difference, that means the gap size between these two energy levels. Okay, so again, I'm going to subtract to find the size of the energy gap between these two levels. 13.6 minus 3.4 is 10.2 electron volts. Okay, so this photon coming in has to have 10.2 EV in order to cause this to happen. Now, what if it has like 10 EV? What if it's not exactly 10.2? Well, it has to be 10.2. Otherwise, what's going to happen is the electron is just going to pass straight through the atom and it's not going to do anything. Okay, so the only photons that matter are the photons that have that exact amount of energy equal to the gap size between two energy levels. The second part of this question says, an excited electron falls from n equals 4 to n equals 2 and emits a photon. How much energy will this photon have? Okay, so here's n equals 4, here's n equals 2. I want the gap size between those two energy levels. So that's going to be 3.4 minus 0.85. Again, forgetting the minus signs because the minus signs do nothing for me. I don't care about that. All I care about is is the size of the gap between the two energy levels. So that should be 2.55 electron volts, and so that photon is going to be emitted because it's going down from a higher energy level to a lower energy level. Okay, so pause there if you need to look at that some more. We're going to do two more examples. Okay. Example 8. Look at the energy level diagram to the right. What is the energy of the photon emitted or released in transition A? Okay, so see if you can answer this question on your own. Take a look at arrow A. What energy would that photon have? Okay, so hopefully you got the correct answer. That is 12.1 eV. I know that because between this level and this level, I'm looking at the gap. The gap between 0 and 12.1 is just 12.1. Okay, so 12.1 electron volts, that's the energy of the photon emitted in transition A. The second question says, state the energy of the photon involved in transitions B and C and explain the difference between these transitions. Okay, so pause it there and see if you can answer that question on your own. Okay, now B and C both involve the difference between levels 2 and 1, and the energy gap there is 10.2 electron volts. And so that's the answer to the first part of that question. Now the difference between transition B and C is transition B is going to involve absorbing a photon. That's where there's a photon absorbed. And C is going to involve a emitted photon. Okay, if you just look at which way it's going, remember the electron is sitting in the ground state. In order to go up to a higher energy level, it has to take in energy somehow. Okay, so it has to absorb a photon. Okay, when that electron is done being excited and it falls back down, it has to give that energy back in the form of a photon. Okay, that's the only difference between B and C. Alright, pause there if you need to look at that, and we'll do one more example. Okay, example 9 says which of the following transitions is not possible? Okay, so let's look at the answer choices. So I'm going to change this just a little bit. Okay, so an electron moves from n equals 5 to n equals 4 by emitting a 0.31 eV photon. Now, this picture I've actually used before. If you look at the numbers from 5 to 4, this gap is 0.31 eV. I just happen to remember because if you look at the numbers, we saw those exact same numbers a few minutes ago. Okay, so A is possible. We can eliminate A as an answer choice. B says an electron moves from n equals 1 to n equals 2 by absorbing a 10.19 eV photon. So again, let's look at the gap between n equals 1 and n equals 2. Okay, 13.59 minus 3.4 is 10.19 eV, and in order to go from 1 to 2, okay, it has to absorb a photon. Okay, so B, we can eliminate B. C says an electron moves from n equals 4 to n equals 2 by emitting a 2.55 eV photon. Okay, so let's look at 4 and 2. I want the gap between 4 and 2. That would be 3.40 minus 0.85. That is, in fact, 2.55 eV, and that is a downward transition, and so that would emit a photon. So we can eliminate C. Now, D is the correct answer. Okay, see if you can figure out what's wrong with D. Okay, so the issue with D is not the number, because the gap size between 3 and 2 is in fact 1.89. The issue is that if you're going from a higher to a lower energy level, the only way that's possible is by emitting a photon, not absorbing a photon. Okay, so that transition is not possible. Okay, so we did a lot of examples. Hopefully that helps. Please let me know if you have any questions. This is going to be the last video as part of summer school. Okay, so I hope that you have learned a lot this semester. Please let me know if you have any questions about anything. Please make sure you get your assignments completed on time. And it's been a pleasure being your summer school physics teacher for this semester, and if you had me last semester, for last semester as well. Okay, so I hope you all have a great summer, and make sure you finish your assignments on time.